All right, thank you for the kind invitation and the kind introduction. I'm excited to be here today talking about some of our work trying to increase accuracy in non-targeted analysis from monitoring data quality to reducing false positives. So I want to start with a quick rundown of kind of the difference between non-targeted analysis, suspect screening analysis, and targeted analysis. And importantly, non-targeted analysis is often used as an umbrella term that covers both non-targeted analysis and suspect screening analysis. So if we kind of start thinking about targeted analysis, that would be looking for things that we know could potentially be in a sample. And so the majority of analytical methods that most people are familiar with are targeted methods. But if you look at the chemical space that actually covers, it's actually relatively small relative to the possible chemical space. So there's a need for things like suspect screening. And so this would be used to look at things like known unknowns. And so what we mean by that is they're chemicals that are known to exist. They exist in a database, or you've built them into perhaps your own database. And so you can screen a sample specifically for those compounds, even if you don't necessarily know that those compounds are in the sample, and even if you haven't necessarily developed a method, specific to those compounds. And so this is often, kind of on the order of hundreds to thousands of compounds. And so this covers quite a bit more chemical space, but still, not all of the possible chemical space. And so that's kind of the area that true non-targeted analysis kind of fills in, is looking at these unknown unknowns. So potentially being able to identify chemicals that might not exist on a known list or database. I also wanted to mention that I'm, stealing this image from the Best Practices for Non-Targeted Analysis Working Group, which is a great group that I've been working with for several years now, developing tools and resources, educational materials, things like that. So if anything I just said, piqued your interest and you want to learn more, visiting our website is a good idea. And so I want to kind of dive into foods, because my research is focused on foods at the FDA. And so there's quite a few challenges, somewhat specific to food analysis, that are worth mentioning. So obviously there's a wide diversity of different sample types. If you think about the foods that you eat even just in a day, they're quite diverse. And so just to give you kind of an image of what that looks like, here's the AOAC food triangle that kind of separates foods based on their relative fat, protein, and carbohydrate concentrations. On top of that, for any one sample, there might be many different brands. And we have done some work in the past kind of proving to ourselves that even if it's the same type of food, but a different brand, they are not chemically the same. And so that can be quite challenging. The number of compounds that we detect is also quite a lot. There tend to be, thousands of compounds detected in any given sample. And so here's an example of orange juice. And so you can see a lot of peaks. And if you zoom in down towards the baseline, you can see a lot of little peaks. So there's a lot of chemical complexity here, a wide range of different concentrations, things like that. And one of the challenges that we face is that the majority of these compounds, if not all, are presumably safe. They're just a typical, if you're looking at orange juice, it's just a normal compound that's found in oranges. That's totally fine. And so from our perspective, where we mainly focus on food safety applications, we need a way to kind of prioritize the peaks that we find to try and go after and try to identify only the ones that we think might be of concern or of interest. And so trying to come up with ways to prioritize that has been a big body of work that my group has been working on. And another way that NTA is really helpful for foods, but also kind of adds to the challenges that we face, is globalization of the food supply. And so, we're importing foods from all over the world, and different countries have different rules and regulations. Things developed in other countries might potentially introduce new chemicals that we haven't seen before, and so NTA can be really valuable in those cases. So non-targeted analysis, data processing is the most time-consuming portion of our work, and so I want to spend a little bit of time talking about what the data processing workflow looks like. And I'm going to start with suspect screening analysis. So we collect our LC-HRMS data, or high-resolution mass spectrometry data, and then this is the case, again, for suspect screening, where you have a database that you're comparing to. So you have a list of chemicals, you probably have their molecular formulas, or at least their accurate masses, and you can mine the data directly for that. So effectively just generating an extracted ion chromatogram for each of the chemicals in that list. And then from there, we try to prioritize the hits that we get. We try to reduce potential false positive hits. This is, I'll kind of come back to this a lot throughout the talk. And then ultimately, you want to end up with a putative identification, and ideally, you would confirm that with a standard. And of course, there are many cases where standards might not be necessarily available or easy to obtain. And so, we have approaches to kind of try to deal with that as well. But in the ideal situation, you would be able to confirm with a standard. So you'd be very confident that you have identified the correct thing. Importantly, quality controls should be used to confirm accuracy. And by this, there's a variety of different quality controls. But one of the main ones that I'll spend some time talking on in a couple slides is standard mixtures. So stay tuned for that. For non-targeted analysis, this is a little bit harder for software to do. So you're not giving it a list of masses to search in the data. You're actually asking the software to kind of go through the data and figure out if there are peaks. And then once it finds peaks, it's going to find a peak for each ion. And of course, every chemical presents as multiple ions via LC-HRMS. And so the software then also needs to interpret those ions and try to group them into what we call features. And so features, when we say that, is effectively ideally corresponds to one compound. So you've grouped all the isotopes, different adducts, et cetera, that might be detected for the same compound into one feature representing one compound. We do call them a little bit differently just because, or we don't call them compounds per se, because obviously this is software and it doesn't always get it right. And so we use software to help us with that, and then we can either use that data as is without actually trying to identify individual components. We can classify samples. Say we just wanted to know whether a sample was adulterated or not. We could potentially do something like that with like a PCA analysis. We can also use this approach to help us prioritize what features need to be identified. For example, if say the samples in the blue circle were making people sick, and these were an available control that seemed to be fine, we could specifically focus our efforts on identifying the compounds that are most responsible for separating the two classes. If we want to do identification, we usually then tend to generate molecular formula based on the mass, and so the more accurate your mass, the better this is, as well as the isotopic fit distribution. And then we go kind of through a similar process as the suspect screening workflow, where we try to prioritize this data, reduce our potential false positive molecular formula or identifications, and then come up with a putative identification, ideally confirming with a standard. And again, QC should be used to confirm accuracy throughout all of these steps as well. The other thing I wanted to mention, I kind of talked about it on the first slide, was that suspect screening is often used as part of the non-targeted approach. It's one of the quickest ways to try and get a lead on what an identification for a compound might be. And so that's why NTA is kind of used as this umbrella term that encompasses both, because most people do some amount of suspect screening as part of their NTA workflow. So today I'm going to focus specifically on the sections of the workflow that we have used the ACDLabs software for. And so I've highlighted those in the pink boxes here. So the next thing I want to talk about, I mentioned on the previous slide multiple times, is using appropriate quality control standard mixtures to be able to make sure that your instrument is performing properly and that each of the steps in your workflow are performing properly. And so we use two different types of mixtures, one with a small number of compounds and one with a large number of compounds. The mixture that we use, the small mix that we use, is actually this Waters LCMS QC RM mix, which we call Waters QC mix for short. So there's 9 compounds. They span a wide range of molecular weights, ionized in both polarities, and they have retention times throughout most of our chromatogram. And so this is helpful for just making sure that the instrument's good, ready to go before we actually start collecting data on our samples. And it also helps us monitor our instrument performance over time. So we can see things like, is our column starting to go bad or things like this. We can also use it as sort of a quick look at being able to validate some of our data processing parameters. So the software that we use is pretty complex. There's a lot of different parameters that you can play with and tweak. And so having this smaller subset of compounds to look for can help us kind of get a quick gauge of how well the parameters we've selected are working. We also use a larger QC mix. And so, inherently this covers a much broader range of chemical space than the smaller mix. And so this can be useful for understanding what types of molecules are extracted well or not with your method. You could potentially use it to try and gauge how many false positives and false negatives you're getting. You can also use it to look at your experimental data quality and help you set thresholds for what you expect the data quality to be for an unknown compound that you're trying to identify. And I'll talk about that in a few slides as well. So a little bit more detail on what's actually included in the standard mixture. So we developed this on purpose to cover a wide range of just different physical chemical properties. So wide range of molecular weights, retention times or log KOW values. We have compounds that ionize in both positive and negative modes, as well as a variety of different responses. We also made sure that we had diversity of elemental composition because we wanted to make sure that we're representing different types of classes of molecules with the standard mixture. And so a lot of the ways that we can use this mixture are for things like performance assessment, defining the measurable chemical space of a method, which is really important. I think there's a somewhat misnomer promise that NTA can tell you everything that's in your sample. But of course, no one analytical method is going to be able to tell you everything. It can't detect everything. And so understanding, if we don't report a certain compound, whether or not we would have detected it if it was there, is helpful to be able to communicate and for decision makers to be able to rely on this data and understand it well enough to actually make a decision. We can also use it to help us compare methods and results across different labs or across different instruments, which is one of the challenges in the community right now with such diverse workflows, which is great. It makes it really flexible and useful in a variety of fields, but it does mean that reproducibility is somewhat of a challenge. We can also use it to develop models such as retention time prediction, which I'll talk about in a few slides, as well as quantitative, non-targeted analysis, etc. We can use it to test new instruments and software, and it's necessary for transferring non-targeted methods to our field labs, which is something that we're actively in the process of trying to figure out right now. So the next steps on this mixture, we're currently working towards commercialization. You can imagine, there's 89 compounds in this mixture and it's kind of a pain to make and takes a lot of time. And we don't have good, stability assessment of it and things like that. So having a commercially available product would be really helpful for the community as well as us. And so we're currently collaborating with NIST to try and make this happen. We've also surveyed the NTA community to see if something like the standard that we developed would fit the characteristics they would need across these different fields to kind of demonstrate that there is a good market for this. And the results of that survey are in an upcoming publication that's actually moving through our clearance process right now, and it'll be submitted to the journal hopefully in the next week or two. So I mentioned that, understanding your experimental data quality is important, and you can use it to set thresholds for your unknown identification. So in this study, we spiked our 89 compound mixture into 3 different food matrices: apple juice, sweet potato, and yogurt. And we found that greater than 98% of these compounds that we spiked in all had mass accuracies within plus or minus 2 ppm. We did a similar look at the formula fit quality, which is effectively a measurement of how well the isotopic fit matches. And we found that greater than 90% of the isotopic fits were greater than 0.6 FFQ. And so we can use this to set a threshold where, say, if we had an unknown with a putative identification, but the mass accuracy was, 4 ppm, we might be less confident that that's really what the compound is. And so this is really helpful. We can also have also done some work to improve some of these data quality metrics. For example, our mass accuracy. So as I mentioned on the previous slide, we typically on our Orbitrap instrument are able to get mass accuracies within plus or minus 2 ppm. But over time, this does drift. So if you had a really long queue, which queues for non-targeted analysis tend to be very long, you've got often, or you should, not everyone does all of these QA/QC processes that you should, but you should have, replicates for each sample. Often there's a lot of samples because you want to have a, statistically significant number of samples to be able to do some of the data processing and analysis on the back end. And so these can be really long queues when including proper QA/QC procedures. And so you can see that our mass accuracy drifts out, and now we're within about negative 3 ppm over a 69-hour long queue. So one of the ways we can address this is by introducing lock mass ions and then having the instrument can recalibrate the spectra on the fly. And so we wanted to understand, develop a method for actually introducing these lock mass ions to the mass spectrometer while we're running. And for that, we use this little steel holder, and then there's space in this holder for 2 sponges, and these sponges are about the size of a pencil eraser. And you can dope your calibrant ions directly onto the sponge. And then there's a little lid with variable number of holes in the lid, such that, to account for like different volatility of those different lock mass ions. And we put that holder then inside the source of our, this is a Q exactive, but any of the thermo instruments so far, probably others as well, but we've only tested it on thermo instruments so far. You can set it right inside the source housing. And just to kind of help orient you in this picture, this is the spray needle and here's the orifice. And of course, the transfer capillary and the gases in the source are all heated. And so this actually does get pretty warm, this housing itself, and that helps to volatilize some of these lock mass compounds. And they effectively just get sucked into the mass spectrometer along with your sample. And so we've done some tests to show that they stay present, throughout even 69 hours. And you can use them then as lock mass. And if we do that, you can see we're actually able to correct our mass accuracies to within plus or minus 1 ppm. And that stays stable then across all the entirety of this pretty long queue. We also tested this on our NTSQC compounds, and we found that about 94% of the compounds were within plus or minus 1 ppm when using this lock mass approach. And to kind of give you a sense of, why does this matter so much? So for every sample, we tend to detect hundreds to thousands of features. And so that's, roughly represented by these peaks here. And then for each one of those features, we can generate, say, 1 to 10 or so molecular formula that could be possible. And so, here's an example of 4 pretty different molecular formula that all have masses very, very close to each other. And so the more accurate you know that mass, the more you can start excluding some of these as possibilities. And then for each one of these molecular formula, you can have tens to thousands of possible structures. And so an example of that, we searched 4 different molecular formula across 3 different databases, and you can see many, many different molecules actually can fit to any one of those molecular formula. So if you were to multiply this out, you might have tens of thousands to tens of millions of compounds to consider per sample, which is just untenable. And so we need ways to try and limit the number of false positives throughout each of these steps to try and help make that more manageable and easier to go through. And ideally, the more information that you have stacked up here, the more you can eliminate false positives. You can drill down to hopefully a single identification with an increase in confidence of that identification. So one of the ways that we can reduce false positives is using retention time prediction. And for this work, we used the Chrome Genius software. And we used our NTSQC mix as our model. And so those are the blue dots here. And then we use that to predict the retention time for 211 other compounds that came from commercially available mixtures of pesticides, pharmaceuticals, mycotoxins, aflatoxins, and amino acids. And so those are represented here by the gray dots. And so you can see there is a decent correlation between the predicted retention time and the experimental retention time. The table over here is meant to kind of show you how we can use this to set thresholds to help us eliminate false positives. So for example, if we set a pretty tight window of plus or minus 1.5 minutes, about a little bit more than 70% of these compounds would have been correctly predicted within that window. And so, this helps us, eliminate false positives, but we also might be kicking out a decent amount of true positives, right? So we can increase that window of allowance and capture more of the correct compounds, but we also tend to then increase our potential for false positives. So there's a bit of a trade-off here. We decided to also test multiple different columns. So the kinetic C18 is the one that I showed on the previous slide. And that's the column that we typically use for our global NTA analysis. But we wanted to look and see if there were any differences in performance across different stationary phases. So we also tested the kinetics biphenyl and the Luna Omega polar C18. And you can see all show pretty good correlation between predicted and experimental retention time. And then if we look over here, so these 2 columns are the kinetic C18, the biphenyl, and then the polar C18. And it looks like if we look at the percent of compounds in each of these retention time windows, it looks like we get a little bit better performance with the kinetics biphenyl column relative to the others, but overall pretty similar. Another thing I wanted to talk about is our ability to do suspect screening with large databases. And so some of the challenges associated here are that, we're talking about a lot of compounds. So by large, I mean greater than 10,000 compounds. And so this requires a significant amount of computational power and time. And so people have taken a couple of different approaches to address these challenges. So, if you think about using a larger, more general database, think maybe like PubChem as a kind of extreme example of this. You are likely to have compounds that you care about in there, but your propensity for false positives is also higher. So in cases where your study goal or scope of your study is a little bit more focused, say if you were only interested in PFAS compounds or pesticide compounds or something like that, you could design the database to be smaller or more focused on specifically the compounds you're interested in. And so this can reduce the amount of time and computational power that it takes to do suspect screening. But it's also possible that you could miss compounds that might be of interest. So we looked at how the processing time changes using ACDLabs Spectris ITA, or IntelliTarget, and we wanted to see, as we increase the number of compounds, how does that change the amount of processing time required? And so obviously, as we move from 5,000 or less compounds up to say 25,000 compounds, our processing time increases significantly. One of the things that we also observed is that we can kind of combine our suspect screening approach with our retention time prediction. And this not only helps us eliminate some of those false positives, but can also reduce the processing time required. So, this gray trace is showing a retention time window of 10 minutes versus a retention time window of 1 minute, because it effectively gives, fewer compounds to have to be searched for across each of the detected peaks. So with that, I'd kind of like to wrap up quickly. So some closing thoughts. Non-targeted analysis using liquid chromatography, high resolution mass spectrometry is a really powerful tool, which is why it's being used across such diverse fields, including environmental analysis, foods, etc. But monitoring QC compounds is critical so that you can understand your data quality and your accuracy. You can set thresholds that can help you reduce false positives. The databases that you use for suspect screening analysis can really impact the result. So, there's trade-offs with database size versus false positives and processing time and power requirements. And then, of course, processing software is really critical to all of the steps of our workflow. And, as I mentioned on one of the early slides, data processing really is the most time-consuming portion of this work. And so it really helps to have good software, such as the ACDLabs software that I've talked about today, to help us make each of those steps a little bit easier. I'd like to give a shout out to Jacob Primo, who was an undergraduate student that helped us develop the NTSQC mixture, as well as to Karen Butler, who is a relatively new to the NTA group that is working with me, and she's kind of taking over some of the suspect screening stuff and coming up to speed on that. As well as my co-authors, both Ann Nolhoff and Brian Ning, who contributed to the slides I presented today. And then I also wanted to mention, again, the best practices for non-targeted analysis group. They're doing a lot of really good work, so if you're interested in learning more about NTA, I hope you'll check out the website, and feel free to ask me any questions about the group. I'm happy to answer those as well. And thank you all for your attention.
Perfect. That looked good on my end.